So in the next section, we're going to talk about some methodologies of how to accelerate data lake house queries. So first, let's talk about raw query performance, right? Firstly, a cache is absolutely necessary for a query engine to have, right? Because fetching data, the process is very slow, right? And that first to overcome the unstable performance of data lake houses, right? And also to save IO cost from fetching the data, from external storage. So make sure that your queries is fast and stable, right? And second is that you want to look for those query engines that has MPP or has in-memory data shuffling, right? Older not query engine, processing engines such as Spark, right? When they do data shuffling, they basically persist all of the intermediate results to disk in order to be stable for a very long running job, right? So let's say a job runs for 4 hours and it breaks at the third hour, so it can continue, right? It doesn't stop from the beginning. But that is good for huge long running workloads, but it's not really good for low latency workload, because anything that touches disk is going to be very slow, right? So you want to search for those query engines that runs completely in memory, thus optimize for low latency, high concurrency queries, right? And also you want to look for those query engines that has good system level optimizations. Specifically, you want to be written in C++, right? And the reason for that is to fully utilize the SIMD instruction sets, right? SIMD instruction sets basically say teaches the CPU, to run everything in batch, and in OLAP, everything is in batch. The more batch you run, the faster it goes. So C++ is absolutely necessary if you want to have the best of the best performance, right? And a lot of the query engines available today are really not optimized for pure query performance, right? They opt for a higher level language to develop, such as Java, which is faster to develop, but it really lacks in performance, right? Because before we didn't really have a lake house, and we weren't trying to to unify all of the workloads on the lake, right? And before it was connecting to a million different data sources, right? And for that purpose, uh, picking a language that's efficient in development is good. But now, if you want to like run really high demanding workloads with that query engine, a C++ engine is absolutely favorable, right? Although Java, like JDK 21, they have a lot of optimizations for SIMD, or like auto SIMD, but it's nowhere near the amount of optimization we can do with the C++ engine, right? So these are some very high level points, but with the right tools, getting data warehouse performance on the data lake house is not only possible, it's actually quite easy to do, right? We're gonna talk about them. I'm gonna show some numbers in the following slides, right? So here, let's compare data warehouse to data lakehouse. And here I picked a query engine that's called StarRocks. StarRocks is an open source query engine, right? The reason I picked StarRocks is because it does both, and it does both really well. It can be a data warehouse where it persists the data, although in a remote storage, in the cloud object storage, but it's its own file format, right? With its own storage engine. So you can do like real-time analytics, right? So it can support real-time upserts, right? For real-time analytics, or you can swap the StarRocks storage engine out with the data lakehouse storage, right? You swap the SARS file format and the SARS table format out with Parquet files and, let's say, Apache Iceberg or Apache Hudi, right? So StarRocks can act like a high performance query engine for the open data lake, right? To get some reference point, let's first look at how fast is StarRocks as a data warehouse. So here is a benchmark of SSB benchmark. So the SSB benchmark basically resemble those multi-table but simpler queries like you would see in like reporting or a BI scenario, right? So there's one thing I want to clear out first. So you can see here you have flat and multi-table, right, on the right hand side. Um, SSB originally is a multi-table test, but ClickHouse, the project, it creates a variant of the SSB benchmark test. So basically, you take all of the tables and perform a denormalization into a big flat table and only query the flat table, and basically remove all of the on-the-fly joins, but keep all of the all of the on-the-fly aggregations, right? So on that variant of the benchmark, StarRocks is faster than ClickHouse and way faster than Apache Druid. And StarRocks on the original multi-table benchmark, SSB benchmark, is even faster than Druid's single table performance, right? And join is a very expensive thing to do. And this is, yeah, this showcases like how fast StarRocks as a data warehouse is, right? So now we have a reference point. Let's do the comparison, right? StarRocks as a data warehouse versus StarRocks as a Lakehouse query engine. So this, to make it more difficult, this is the TPCDS 1 terabyte benchmark. So instead of simpler queries, so this resembles the queries of, let's say, ETL workload or and a pretty complex, a more complex ad hoc query, right? So a lot of joins between large tables, and also a lot of high cardinality aggregations, right? And this is run on the same exact hardware between StarRocks as a data warehouse and StarRocks as a query engine, right? And those are both hot queries. The data warehouse solution is only 12% faster, which means that you gain all of the benefits of a data lake house. Unify all of your data in one place, keeping only one copy of the data, right? And not maintaining a billion different data warehouses, not have data scattered around, and only at a cost of 12% of the performance. And here's another comparison from StarRocks to another query engine called Trino. Trino is pretty fast, and this is on TPCDS, and StarRocks is 5.5 times faster than Trino on this, right? So this showcases basically um, just by querying, right? No pre-computation involved. It's completely possible to have data warehouse like performance on the data lakehouse, right? So you can have those benefits of the data lakehouse while not really losing much performance. And then let's circle back to the ETL problem, right? To the ETL problem. There's one thing that has been going around in the industry is that a materialized view with full query rewrite, and this functionality can help we solve the on-demand pre-computation pipeline challenge we talked about before, right? A materialized view is basically a stored result of a query, right? And it's managed by the query engine itself. So a query rewrite is that when you write a query, it directly points to the materialized view, so you don't have to change your SQL script, right? With when you try to do pre-computation. So this solves the problem talk about with Spark, right? So the benefit is enormous, right? So you gain the flexibility of on-demand query acceleration, right? So you can default to querying the original table schema, right? And then use materialized views to fix those slow queries. And this gives you better user experience for data users because they don't really feel anything, right? Because they don't really need to change the SQL script, right? And that saves compute and storage from unnecessary pre-computation pipelines because you only build them when you need them, right? And ultimately, you go production a lot faster.